We'd like to welcome Professor... Oh, I was looking for you over there. You've gone. Marilyn Goose. Marilyn is a Professor of STEM Education and Director of EpiSTEM at the National Centre for STEM Education, a department of the University of Limerick and Ireland. Marilyn is internationally known for her work with digital technologies and was instrumental in changes that have taken place in Australia, her home country. Her role as ICMI Vice President brings her into contact with colleagues all over the world, and I'm sure she will have some great stories to tell us. So please, can you come up, and thank you very much for doing that great MOOC that I've just signed up for.
Thank you. Thanks very much. I have a feeling that I'm not going to be too alternative. I think I'm going to reinforce a lot of the things that Alison has said. And I'm going to begin with a little bit of historical context, which I know will be familiar to many people in this room. And I am going to talk a little bit about ICMI, the International Commission for Mathematical Instruction. So ICMI commissions studies every few years on topics of current interest in mathematics education. And these studies are built around an international conference which leads to production of a study volume, which promotes discussion and suggests future directions for the field. And it happens that the very first ICMI study was on digital technologies in mathematics education. And if you read the study volume, you can see that it presented a very optimistic view about how technology would be transforming mathematics education. About 20 years later, the 17th ICMI study revisited this topic, and Celia was one of the co-chairs. I know people here, and hello Zolt, I know you were there as well at that conference. And one of the things that came out of that conference and is represented in the study volume is we realised that change had happened a lot more slowly than was first anticipated 20 years ago. And we realised, I think, that to integrate digital technologies into mathematics education at a large scale, as Alison has pointed out, is an enormous challenge for a whole lot of reasons. At the time of the first ICMI study, what was research looking at? Well, it was focusing very much on the technology itself and its mathematical potential. It was looking at how students were thinking when they were working with technology. So what was missing? What was missing was inquiry into teachers' practice, into the institutional context in which they worked, and into, the reason why we're here, curriculum change. So if technology is going to provide opportunities for transforming curriculum, pedagogy and assessment, there are some things that we need to understand better. And these are the things that I wrote in the beginning of the chapter that I co-authored for this study. And I think these are just as relevant today, even though it's 10 years old now. We need to know more about the teacher's role in these new learning environments. We need to understand what are the kinds of things that influence how and whether teachers use technology. But today I'm going to concentrate on just that last point there. How do we identify whatever effective use is? And what does progress in technology integration look like? So I'm going to just give you a tiny little snapshot. One possible way of mapping progress, and I didn't invent this, this was created by two of my Australian colleagues, Robin Pearce and Kay Stacey. And they proposed a taxonomy that you see here of pedagogical opportunities that might be afforded by using, well, they were using mathematical analysis software, but maybe we could use it for other kinds of technology as well. So you could imagine you could use this for designing lessons, you could use it to map current practice, you can also use it to trace changes in the things that teachers might do and might learn. So just to take you through this map, it's identifying opportunities that might arise at three different levels when teachers are thinking about things. So the level you see highlighted there is thinking about tasks that teachers might set for their students. So, right, we know that technology can be used to increase speed, improve accuracy, give students access to different kinds of mathematical representations. And then we go up to the next level. And teachers might also be thinking about ways in which technology can change classroom interactions. For example, using technology to improve the way that mathematics is displayed and to display it in a way so that everyone can see it in a dynamic sense. the way in which students will use their handheld devices to support their collaborative work. You know, they'll exchange their handheld devices and cluster around those screens, even if they've each got one. And then the next level is thinking about how the subject itself might be transformed. So can technology be used to support new goals for the curriculum, as well as new approaches to teaching mathematics? So I'm going to use this map to look at one tiny little classroom snapshot. And it might not look like a terribly interesting way of using technology, but I think there's something interesting that's come out of it. So this was a Year 12 classroom in Australia. Year 12 is the final year of secondary school. Students are about 17 years old. And all of the students had their own handheld mathematical analysis software device, CAS calculator. This was the task the teacher said. It's a very standard task. When will a population of 50,000 bacteria become extinct? If the decay rate is 4% per day. So there was one pair of students we saw who developed this exponential model for population Y at time X. All right, so far so good. But they then set Y equal to 0 to represent extinction of the population. There are none left. And they entered that into their calculator to try to solve it. And you know what they saw? The worst thing you can possibly see on a screen? It's false. Don't you love those error messages that tell you you're wrong, but don't tell you why you're wrong? The most frustrating thing. So I'm sure you can guess what the students did. They thought, oh, we've made a mistake in keying in the syntax there. So, you know, it's like technology. If it doesn't work, you just bash it a few times. So type it again, type it again, type it again. Oh, we keep getting false. So then they tried different kinds of structures for the syntax, still getting the same error message. So eventually they called the teacher over and said, can you please help? We don't know what we've done wrong. So he looked at the display and he said, there's nothing wrong with the technical side of what you're doing, but you need to think harder about your assumptions. And then he did the teacher thing and he walked away and let them think a little bit longer, didn't give them the answer. So you know, they were thinking and talking and they couldn't work it out. So when the teacher came back to check on them and realised that they really are stuck, he also realised this was an opportunity, a really important pedagogical opportunity for him to focus the class on something that mattered mathematically. And so he got them to display the screen, there was a class discussion. Eventually one student said, you can't have an exponential equation equal to 0. Oh, right. But even so, it still didn't end there. Because they then had to work out, well, what kind of assumption can we make to model extinction if we can't make it 0? So eventually, the students decided that it would be okay to define extinction as any number that was less than 1. And so they entered that into their calculators and that was fine. You know, okay, they got the thing solved. So if we go back to this pedagogical map and think about what was going on, all right, maybe it's sort of focusing on the task, but I think there's something else going on here as well. And it was very much the teacher who took advantage of this opportunity. I think what he did there was, within that space of the lesson, to do something about refocusing the goals of the course on the mathematical modelling process. So it's not just about punching things into a calculator, it's really highlighting the idea that assumptions are important in modelling. So I think there's something going on there at the level of the subject and how it might change. But I don't think, and maybe I'm wrong here, I don't know, I don't think that's where most current research is looking. So let me see if I can kind of justify that. And I'm going to be very parochial and just take an Australasian view here, but that's okay because I'm Australian. So this is a recent review of research in mathematics education in Australasia. It's published every 4 years by MERGA, the Mathematics Education Research Group of Australasia. This is from 2012 to 2015. And there was a chapter in there on digital technologies. And it happens that the authors of that chapter used Pearson Stacey's pedagogical map as the conceptual framework for their review of research. So I thought, I wonder what they found. Should know, I co-edited the book, but I wasn't responsible for that chapter. So I thought I better do something really quick and dirty here. So I just counted the number of pages that were devoted to research studies at each of those 3 levels: task, classroom interactions and subject. And you can see what I found there. So there were 7 pages of studies that were focusing on new kinds of tasks, 4.5 pages looking at research on how classroom interactions had changed, and only 3 pages on studies looking at how the subject of mathematics itself could be transformed. So, I don't know, maybe there's something going on there. I also want to think about where the curriculum emphasis is. And again, I'm going to look at the curriculum I know best, which is the Australian curriculum. It's kind of interesting because we've only just recently produced our first ever national curriculum in Australia. It used to be state-based curriculum. So, I was sort of involved in this whole process that went over several years. Right at the start, there were a number of documents that were written that were kind of shaping up the curriculum. So here is some words from the SHAPE document that laid out what the role of digital technologies might be. All right, explaining and presenting mathematics, connecting representations, deepening understanding, all of those very positive things. But again, if we look now at what the curriculum is like, I can only echo what I think Lynn was saying this morning. It looks like what it was like in the 1960s. So, what's changed? The curriculum goals and methods, sequencing of content have not changed one little bit, despite the sort of bolting on of nice words about technology there. So, what I can see is that the pedagogical opportunities that are there exist mainly at the level of tasks, transforming tasks that are offered to students. So, I think that's actually a lost opportunity there when it comes to digital technologies. So this is my last slide. I'm going to come back to the ICMI 17 study. Here are the things that I wrote at the end of this chapter that I co-authored. Some questions that I hoped would make people think for a while. Now, it's 10 years ago. I think we still need to think about these questions. If we're thinking about progress in technology integration, how do we define progress? What is it that changes or gets better? And there's a few things there that might change. What do we mean by better? And for whom might things be better? How do we know things are better? That's a question of methodology. And by what means might we, awful word, measure evidence that change has happened? And then finally, if we can see some change, how can we explain it? And that is a matter for theory. And that's where I'm going to end. I hope you find those questions stimulating as well. Thank you.